We introduce view birdification, the problem of simultaneously recovering ground plane movements of the observer and pedestrians given an egocentric video of an observer walking in a crowd. This enables human behavior analysis from on-ground perspectives of a person, a robot, or a self-driving car. View birdification can be considered as a special case of SLAM, but these two are fundamentally different. In conventional SLAM, we recover the camera ego motion by observing static K-points from multiple viewpoints. However, such static K-points are often occluded. Hard to find and track in cluttered dynamic scenes such as in a dense crowd. See the video on the right. Static landmarks cannot be reliably detected and tracked due to severe occlusion. In contrast, in view birdification, we require no static K-points and can reconstruct both ego motion and surrounding dynamics only from their observed motions in the ego view. We achieve this by introducing two key ideas. First, we assume that observed moving targets are all pedestrians with a known height distribution. That is, the positions of pedestrians on the ground plane can be constrained along the lines that PSS through a center of projection. Second, the motion of observed moving targets are not arbitrary, but conform to known crowd motion models. The interaction of pedestrians' movements in a crowd can be locally described with analytic or data-driven models. We formulate view birdification as a geometric trajectory reconstruction problem, and derive a Bayesian cascaded optimization consisting of a prior that represents crowd interaction model, and a likelihood that represents the pedestrian observation model. In observation model, we assume a perspective projection model or a cylindrical projection model. Given detected bounding boxes in the image plane, we can estimate the 3D location on the ground plane by inverse projection. However, the true height of each pedestrian is unknown. To model uncertainty arising from the variance of pedestrian heights, we assume that heights of pedestrians follow a Gaussian distribution. That is, since the scale and difference of human heights are proportional to estimated geometric depth, the positions of pedestrians on the ground plane can be constrained along the Gaussians on the lines that pass through a center of projection. As prior, in crowd interaction model, we can use analytic or data-driven models which represent how pedestrians will move next on the ground plane. Although we show social force model here as example, any type of model including data-driven models can be incorporated to our method. The optimal on-ground positions of pedestrians and the camera can be obtained by maximizing the posterior probability consisting of these prior and likelihood. Taking negative log probabilities, the problem can be expressed as minimization of energy functions for estimating positions of the observer and in-view pedestrians. We first solve for the camera ego motion with gradient descent, and then localize each pedestrian by solving a combinatorial problem with constraints that encode proximal pedestrian interactions. So view birdification can be solved by first estimating the ego motion and then recovering the relative locations between the camera and the pedestrians. We construct 3 datasets to validate our method. The first 2 use simulated pedestrian trajectories computed from a crowd simulator, or real pedestrian trajectories extracted from real crowd videos. The videos render pedestrians as stick figures. For the third dataset, we use a game engine to render photorealistic egocentric videos of simulated pedestrians. Here quantitative results on the real crowd dataset with synthetic ego views. Our extensive evaluation demonstrates the effectiveness of our method for crowds of varying densities. Contrary to the conventional SLAM which collapse in cluttered dynamic environment, in our method, the more crowded, the more certain the camera position can be estimated. Here's another results on the game engine dataset. Our method successfully birdifies the movements of the observer and surrounding pedestrians on the ground plane. As long as the observer sees a few people in his egocentric view, the method can continuously localize him and his surrounding pedestrians even in a dense crowd. Our geometric view birdification does not require any static background. In contrast, SLAM fails when static K-points cannot be reliably detected and tracked. Our method successfully birdifies the views even in those challenging cases. To further validate the applicability of our method in the feasible configuration, we leverage the real robot dataset, which includes the panorama RGB images with 2D/3D bounding box annotations of pedestrians captured by a mobile robot platform of human-compatible size. Our method successfully reconstructs the movements of the observer and surrounding pedestrians even if the ego motion model does not conform crowd motion model. Please see the paper for more details. Thank you for watching.